Okay, let's begin then. So today we want to discuss angles in a polygon and also angles in a circle, circle properties. These are two things that I want to do today. In the last session, we talked about these properties that you would have to use in case of polygons and circles as well. So you need to keep them in mind. And the sum of all angles at a point is 360. Sum of all angles at a point in a straight line, that is 180. Vertically opposite angles are equal, and then for angles with parallel lines, there's some properties that we need to know about. First of all, we have corresponding angles. They are equal. Alternate angles are equal, and then co-interior angles. These two angles, they are supplementary, which means that their sum is supposed to be 180 degrees. And in general, whenever you have two parallel lines like this, you can remember all the acute angles that you get with this third line, they're going to be equal to each other, and all the obtuse angles that you get with this third line that's passing through those parallel lines, they are going to be equal to each other as well. Okay, so that is what we did in the last session. Now, let's start with angles in a polygon now. Let me adjust my pen sizes quickly and then we begin. Okay, so angles in a polygon. So now, first of all, what is a polygon? Polygon is basically any shape that consists of straight lines. It's a closed shape consisting of straight lines. Let me write that down. A closed shape consisting only of straight lines. Now, in this word polygon, poly basically refers to many, that you can have many, gon, which refers to both sides and angles. So it's a closed shape that has many sides and many angles. Okay, that's a polygon. Now, you've seen many polygons before. For example, triangle is a polygon. A quadrilateral is a polygon. Quadrilateral is any figure that has four sides: square, rectangle, trapezium, parallelogram, rhombus. All of these are types of quadrilaterals, right? So quadrilateral is a shape that has four sides. Then you can have five-sided figures like pentagon, six-sided hexagon, seven-sided heptagon, eight-sided octagon, and so on. So it's basically a general name that we give to all of those different shapes consisting of different sides. Now, the number of sides that we have in a polygon, we often refer to that by n, okay? So number of sides is often referred to by the letter n. So n is going to refer to number of sides. Now, if you have a polygon that has three sides, what do we call that? We call that a triangle. Okay, if we have n equal to 4, we call that a quadrilateral. There are a number of different quadrilaterals that you've seen. As I told you, for example, it could be a square, it could be a rectangle, it could be a rhombus, a parallelogram, a trapezium, right? Any of those shapes and more. These are examples of quadrilaterals, right? So any figure that has four sides, okay? That's called a quadrilateral. You need to be familiar with these names as well. Okay, so triangle and quadrilateral. Then you have a pentagon. When n is equal to 5, this figure, we call this a pentagon. Penta means 5. Gon, 5 sides, 5 angles. Okay, then if n is equal to 6, it's a hexagon. You need to know this name as well. Hexa refers to 6, and there are 6 sides in this. N equals 7, it's called a heptagon. Again, hepta means seven sides or seven angles. And then n equals 8. That's called an octagon. This is something that comes up quite often. Hexagon, octagon, pentagon. You will see these quite often. Then you have one with n equal to 9. That's called a nonagon. 9 sides. Okay. And then finally, for 10, we have this figure called decagon. And you can have more sides than 10 as well. But these are some names that you do need to remember. Now, some are more important than others to remember. But apart from heptagon and nonagon, the others will be very frequently tested. Okay, so you need to know all of them basically. But heptagon and nonagon, even if you forget them, uh, they would generally mention the number of sides in that figure if they do mention that. But for the rest of these polygons, you do need to remember their names and the number of sides that each one of them has. Okay. Now, n is going to refer to number of sides here. Now, triangle, we're already familiar with. Quadrilateral could be any four-sided figure. Let me show you a quadrilateral. Let's say you have a figure like this. Now, it does not have to be a standard shape. It could look something weird like this as well. How many sides does it have? It has 4 sides. It's an octagon. It's a quadrilateral, right? Because it has 4 sides. This is a quadrilateral. Okay. And then any figure that has 5 sides, that's pentagon. Any figure that has 6 sides, that's any figure that has 6 sides, that's a hexagon, and so on. Okay. Let me show you another figure. Again, a random figure like this. Now, this is a shape that has 5 sides. We would say this is a pentagon, right? So it does not have to be a standard shape. It's just about the number of sides and the number of angles. How many sides does this figure have? It has 5. It has 5 sides. It has 5 angles as well inside. This is a pentagon, and so on. You can have all of those figures like that. Okay, so these are some terminologies that you need to know of, some names of these polygons that you need to be familiar with. Then there's something that we call a regular polygon. A regular polygon. Now, what is a regular polygon? A regular polygon is a polygon that has number 1, all sides equal, and number 2, that has all angles equal. Okay, it should have all sides equal and all angles equal. Now, for regular polygons, there's some names that you need to remember as well. For a triangle, for instance, when n is equal to 3, if all sides are equal, what's that triangle called? That's called an equilateral triangle. Okay, so when you have an equilateral triangle, we can say that's a regular polygon. Okay, because all sides are equal, all angles are 60 degrees, they're all equal to each other as well. When it's n equal to 4, if you have a quadrilateral in which all sides are equal and all angles are equal, what does that mean? All sides are equal and all the angles are going to be 90 degrees. 360 is the sum of all angles in a quadrilateral. And if the angles are 90, what shape is that? That's always a square, right? So if n is equal to 4, if it's a regular polygon, that would be a square. For all the rest of them, n is equal to 5, n equals 6, n equals 7, we don't have any specific names for them like we do for a triangle and square. whatever is the name of that polygon. For example, in case of a pentagon, we just add regular with that. So regular pentagon, and then similarly, you would say regular hexagon, regular heptagon, regular octagon, and so on. Okay. So you need to remember these names. And when we say it's a regular polygon, what that means is all sides and all angles in that polygon, they're equal to each other. Okay. Now let's take an example of a regular polygon. Or in fact, let's talk about regular polygons later. Let's take an example of a general polygon, any polygon. And let's suppose we have something like this. Okay. Now it's a five-sided figure. It's not a regular polygon. It's just a random pentagon, right? It does not have all sides equal or all angles equal. It's just a random pentagon. Now in this pentagon, we have these five vertices. A, B, C, D, E. These are called vertices of the polygon. Now, at each vertex, you have an angle. These angles that we have inside the polygon, these angles are known as interior angles. Okay, the angles in green, let's call them. Okay, let's not name anything, but these green angles, these are called interior angles. Let me just write them on the side. The angles in green, we call them interior angles. Okay, so these are interior angles of a polygon. If you extend any one side of the pentagon outside the pentagon, for instance, if you were to extend this side that's touching this the pentagon at A, if you extend it like this, the angle that is outside the pentagon here, so this is the interior angle. The remaining angle with this line, this outer angle, this is not known as an exterior angle. Okay. Now you can think of the exterior angle from this side. In that case, you would say the other exterior angles. If this is one exterior angle, on the other side, you could say you have this exterior angle. Similarly, here you could say you have this exterior angle. On the other side, you have this exterior angle. And then finally, if you extend this side here as well, this is another exterior angle. The angles that you see in orange, these angles are known as exterior angles. These angles are known as exterior angles. How do you get exterior angles? If you extend any one side outside the pentagon, like this, the angle that you have on the outer side here, this is called the exterior angle. Now, for any one particular vertex, the interior angle that you have and the exterior angle that you have, their sum is always 90 because these are angles in a straight line, right? So this angle, this line here, it's a straight line and it has two angles in it. Both of these angles, their sum is supposed to be 180 degrees. So if I were to call this angle X and this angle Y, what's their sum going to be? X plus Y. That is going to be equal to 180 degrees. And that's true for all the other angles. Now, these angles are not equal to each other, as in this is not necessarily going to be X because it's just a random a pentagon, the angles are not all equal. But for any one vertex, if I call this angle A and this angle B, for this vertex, I can say A plus B, that is going to be 180 degrees. And similarly, if I call this angle C and this angle outside D, then the sum of C and D, that should also be 180 degrees. So if I add up the interior and exterior angle at any one particular point, the sum is always going to be 180 degrees. Okay. So the angles inside the polygon, they're called interior angles. The angles on the outside here, these are called exterior angles. Now, there are some properties that we have for these interior angles and for the exterior angles that you need to be aware of. Remember these figures, triangles, quadrilaterals, we know what's the sum of angle inside these figures. For a triangle, for instance, we know that when we add all the sides, the sum of all the angles for a triangle is 180 degrees. Let me write that down here. For a triangle, we know that the sum of all angles is equal to 180 degrees. Similarly, when you have a figure that has 4 sides, that's a quadrilateral, like a square, rectangle, rhombus, parallelogram, trapezium, all of those shapes, and more that have 4 sides. All of those shapes, if you add up all the angles, for example, in a rectangle, all angles are 90. If you add up all of them, what's the result that you get? 360. Sum of all angles in a rectangle or in any quadrilateral, that is 360 degrees. Now, if you extend this to polygons with more sides, like n equals 5, n equals 6, and so on, you will find that for n equals 5, this is 540. For n equals 6, it's 720. For n equals 7, it is 900, and so on. What happens is, when you add each additional side or each additional angle, the sum of angles increases by 180 degrees, right? For each additional side and for each additional angle, the sum of angles increases by 180 degrees. Now, this actually gives us a general formula, and that general formula looks like this. For any polygon that has n sides, the sum of angles that is given by n minus 2 times 180 degrees. That's the formula that we have for sum of angles in a polygon. Sum of all angles in a polygon. This is given by n minus 2 times 180 degrees. Okay, this is one formula that you need to remember here. Sum of all angles in a polygon, that's n minus 2 into 180. Now, which angles are we talking about, by the way? We're talking about interior angles. Okay, so let's be more specific here. We're talking about sum of all interior angles in a polygon. So basically these angles, the ones in green, if you add all of them up in a pentagon, for instance, you can find the sum of angles using this formula. It's going to be n minus 2 times 180. Sum of all interior angles in a polygon, that's given by n minus 2 times 180. You can try this for any of these polygons. For example, if you input n equal to 3, what do you get from that? If you input n equal to 3, the result is 3 minus 2 times 180, and that gives you 180. If you do it for n equals 4, you get 4 minus 2 times 180, and that gives you 360, and that's also correct. If you try it for n equals 7, for instance, what do you get? You get 7 minus 2 times 180, and the result is 900. That's exactly what we got here as well when we kept adding 180. So if you have to find sum of angles for any polygon, all you have to do is use this formula, input the value of n in place of this. Okay. Then we also have a formula for sum of all exterior angles. Sum of all exterior angles in a polygon. Exterior angles in a polygon. In fact, it's not a formula, it's just a fact. Sum of all exterior angles in a polygon, that always equals 360 degrees. Sum of all exterior angles, it always equals 360 degrees. Basically, what happens is, if you start a quadrilateral at a certain point, for example, if you start from A and you go like this, you go to this side, and then you go this side, this side, this side, this side. So basically, wherever you're starting from, at the end, you eventually come back to the same point. So it's kind of, you can kind of think of in a way that you are completing one full circle, right? You start from one side and then you come back to that same point again. And we know when we complete one full circle, the total angle is 360, right? So we are completing one full cycle starting from that point and we're coming back to that point again. The sum of all the outer angles, that since you've completely turned around 360 degrees, the sum of all exterior angles, that is 360 degrees. Okay. Now, this is the fact that you need to remember. Sum of all angles in a polygon, that is given by 360 degrees. Now, these things are true for any polygon, for a regular polygon, for a non-regular polygon. It's these two formulas are always true. Okay. Let me write that down here. This is about angles, sum of angles in any polygon. Okay, that's given by this. Now, in any random polygon, we cannot find the angle of one particular point if we do not have any additional information. For example, it's a pentagon. We know that the sum of all angles is going to be 5 minus 2 times 180, which gives us 540. That means if I were to add all of these green angles inside, their sum is going to be 540. But I don't know what the value of X is going to be, what the value of A is going to be, what the value of C is going to be. These are all different angles. We don't know what each particular angle is going to be. However, if it was a regular polygon, what's a regular polygon? In a regular polygon, all sides are equal and all angles are equal. If it's a regular polygon, what we can also do is we can find each particular angle in that polygon. Let me write that here. Each angle in a regular polygon. Using these formulas that I wrote above, we can actually find each angle in a regular polygon as well. So if you want one interior angle in a regular polygon, you know that the sum of all the angles is n minus 2 times 180, right? This is something that's something that you know already, n minus 2 times 180. But if it's a polygon that has n sides, and you want angle at one particular side, how can you find that? You can just divide that by n, right? So if it's a pentagon, for instance, and the sum of all angles is 540, now there are 5 angles, you just divide that number by 5, and that will give you each particular angle in that polygon. All right. So for finding one interior angle in a regular polygon, you can use this formula n minus 2 times 180 divided by n. And if we talk about one exterior angle in a regular polygon, again, we know that the sum of all exterior angles is 360. If the sum of all exterior angles is 360, what about one particular exterior angle? The sum is 360. If it has 5 sides, for instance, you divide by 5. If it's n sides, you divide by n. Each exterior angle in a regular polygon is given by this formula 360 divided by n. Okay? You just need to remember these two facts. For a regular polygon, if you want to find one particular angle, just remember you can just divide this by n. And similarly here as well, you can divide this by n to get each particular angle in that regular polygon. These are just the 4 things that you need to remember here. You need to remember the names of these figures. You need to understand what a regular polygon is, has all sides equal and all angles equal. And then these formulas, in sum of interior and exterior angles, that is 180 for at one particular point. And sum of all interior angles in a polygon, that's given by n minus 2 times 180. And sum of all exterior angles is just 360 degrees. And if you want one particular angle in a regular polygon, you just divide those numbers by n. Let's look at a couple of examples in this quickly and see how this will now be applied. Okay, so let's look at this now. It says, in this diagram, the 9-sided polygon has 6 angles of x and 3 angles of y. Now, what's a 9-sided polygon called? We said it's called a nonagon. As I said, it's not used a lot. That particular word is not used a lot in the questions. They've explicitly said it's a 9-sided polygon. So you know n is equal to 9. Now they're saying the n-sided polygon has 6 angles of x and 3 angles of y. Now, is it a regular polygon? It's not a regular polygon because all angles are not equal. Okay, it's not a regular polygon. Okay, now the first part is about symmetry. We will talk about that later when we do symmetry. Let's look at the second part of this. It says, show that the sum of the interior angles of a 9-sided polygon is 1260. How do you do that? What's the formula for this? Sum of interior angles. What's the formula for sum of interior angles? That's n minus 2 times 180. That is 9 minus 2 times 180. When if you evaluate that, you would get 1260 from that. That was this part. Okay, fairly straightforward. Now they're saying find an expression for y in terms of x. Now look at that diagram that we have. We have 6 angles of x and 3 angles of y. We know that the sum of all angles is supposed to be 1260. If there are 6 angles that are x, we can say that's 6x. And then 3 angles that are y, that's 3y. If you were to add up all of them, the result should be 1260. And then you can make y the subject. They're saying find y in terms of x. So how can you do that? You can just make y the subject now. That gives you 3y equal to 1260 minus 6x. And now, if you divide the whole thing by 3, 1260 over 3, that would be 420 minus 6x over 3, that's 2x. This is y in terms of x, y equals 420 minus 2x. Okay, so that's how you could use that in this particular question. Then in the next part, just say, given also that y equals 12 plus x, find x. You would just input y equal to 12 plus x here and solve that equation. That's fairly straightforward. We've done that in coordinate geometry. Let's look at another quick example. Let's do one from the other one, which might be a bit more complicated. Okay. show that the interior angle of a regular decagon is 144 degrees. What's a regular decagon? Decagon is a figure that has 10 sides. So n is equal to 10, right? It's regular, that means all sides are equal and all angles are equal. What's the sum of all angles in a decagon? N minus 2 times 180, right? That will be 10 minus 2 times 180. That's the sum of all angles. What would one angle be? We divide this by n, that is 10. And that should give us 144. You can try that. That's the result that we should get from that, 144 degrees. Now it says AB and BC are two sides of a regular decagon. Okay, so we have AB and BC. These are two sides of a regular decagon. And then they're saying AB and BD, that's this side and this side. These are two sides of a regular hexagon. Decagon is a figure that has 10 sides. Hexagon is a figure that has 6 sides. They're both regular. That means the sides are all equal. The angles are all equal. We need to work out the value for x. How can we do that? We already found that this interior angle for the decagon, this has to be 144 degrees. You can do the same thing for the hexagon. Find this interior angle for the hexagon. How can we do that? We can say hexagon has 6 sides, so that will be 6 minus 2 times 180, right? That will be sum of all angles in this hexagon. Since it's a regular hexagon, we can divide that by the number of sides, which is 6, and that would give us one angle in this hexagon. Let's see what that turns out to be. 4 times 180, that is 720. 720 over 6. Let me just do that quickly here. This is calculator paper. Save time. 720 over 6, that's 120. That means this angle here is 120. So what's this remaining angle then? Angles at a point, they add up to 360. So we know that this angle is going to be 360 minus 120 minus 144, and that gives us 96. Let's confirm that 360 minus this and minus 144, that's 96 degrees. The value of x therefore should be 96 degrees. Okay. Now let me see if I can find one on an exterior angle. Okay. Each interior angle of a regular polygon is p times each exterior angle. Okay, now it's a regular polygon. Each interior angle is p times each exterior angle. Find an expression in terms of p for an exterior angle. Okay, now how do we think about this? Remember, for each interior angle and each exterior angle, their sum is going to be 180. So if we have a polygon that looks like this, such that this is an interior angle and outside this is the exterior angle, their sum is going to be 180 degrees. So we know that sum of these two angles, that's going to be 180 degrees. Now, they're saying each interior angle is p times each exterior angle. So that means interior angle is p times the exterior angle. What we need to find is an exterior angle in terms of p. How can we do that? In place of I here, I can input p times e. In place of I can input p times e. Let's see what we get from that then. Okay, sorry about that. Yeah, over here. In place of I, we can input p times e, and that becomes pe plus e, that equals 180. Make e the subject. If you take e common on the left side, you get e times 1 plus p, that equals 180. And this is going to result in each exterior angle being 180 over 1 plus p. That's what you write here. This is each exterior angle in terms of P. Okay. The number of sides of the polygon. Okay, now how do you figure this out? The number of sides of this polygon. That's just one mark. Let's think about this. Interior angle is this, right? And we know that each interior angle is supposed to be P times each exterior angle. Okay, we have to find this in terms of P as well. Okay, so it has to be in terms of P. We can't find the actual number. It has to be in terms of P. Number of sides of the polygon. Now, how do we think about this? It's a regular polygon. What do we know about a regular polygon? What is each exterior angle? What's each exterior angle of the polygon? It's 360 over n, right? Each exterior angle of a regular polygon, that's given by 360 over n. In the previous part, we found that this angle is 180 over 1 plus p. So we can equate these two things, right? We discussed this formula for each exterior angle, for one exterior angle in a polygon. We said that should be 360 over n. And here we see, in the first part, we found that it's 180 over 1 plus p, so these two have to be equal to each other. How do you find the value of n from this? You can cross multiply, and that will give you 360 times 1 plus p divided by 180 here, and I can take n to the other side. 360 and 180, they get cancelled, and you have 2 left here. So n equals 2 times 1 plus p. You can write that as 2 plus 2p. That's n. That's the number of sides of this polygon. Okay. Any problems with this? Any questions? Any questions on this, anyone? No problems? Okay, good. All right, so that's about angles in a polygon. Now let's discuss circle properties next. Angles in a circle. Now we can discuss the properties today, and then we can do some more practice in the next class on circles then, inshallah. Let's see. We should be able to complete the properties at least, and then we'll have a look at some questions. And if we need to do more practice, then we can do that in the next class. So we talked about angles in a polygon, right? Now let's talk about angles in a circle. So there are a number of properties that you need to know for angles in a circle. Okay, that is what I want to discuss next now. Angle properties in a circle. Now, before we do any of that, there's some terminologies again that you need to be familiar with. Okay, with respect to a circle, there's some names that you need to know. So if we have a circle like this point is the center of the circle, right? That's kind of obvious. Now, if you have a line that is coming from the center of the circle to the circumference of the circle. Circumference is this boundary of the circle, right? This is called the circumference. If we have a line coming from the center of the circle to the circumference, this line is known as the radius. Okay. If you have any random line in a circle that cuts the circle at 2 points, any line that cuts the circle at 2 points. For instance, let's say I have a line that looks like this. This has a name. We call this a chord. Okay, now I can't write that here. I'll just do it like this. So I can write on this. Any line that cuts the circle at 2 points. Straight line that cuts the circle at 2 points, we call this a chord. Okay. And then if you have any line, any chord that passes through the center of the circle. So this is also a chord, right? However, this particular chord, it passes through the center of the circle. This is known as the diameter of the circle. This is the diameter of the circle. And then if we have a line that's going like this, such that it just touches the circle at one point, like this, for instance. It just touches the circle at one point, and that's it. This line is known as a tangent to the circle. You need to be familiar with all of these different terminologies. Chord is any line that intersects the circle at 2 points. Radius is a line coming from the center of the circle to the circumference. Diameter is any chord that's passing through the center of the circle. And a line that just touches the circle at one point like this, we call that line a tangent. Okay? And then there's one more thing. If we have a circle like this, and the circle is divided by a chord, any chord like this. These two regions that you see, one region here and another region here, the chord divides your circle into these two separate regions, right? One in yellow and the other in blue. These two regions, we call them segments. These regions are called segments. The bigger one, we call this the major segment. And the smaller one here, we call this the minor segment. But this name is important, segment. These are called segments in a circle. It's different from a sector. Sector is something else, which although we will not need to use in this topic, I'll just tell you about that because we will need that later when we do mensuration. That will most likely be next week, inshallah, or the week after that. This is the segment. It's different from a sector. What's a sector? Sector is not made up of just one straight line. Sector is made up of two radii, two radius coming from the center of the circle like this. So if we have two radius coming from the center of the circle, this shape that you get, this is called a sector. A sector has three sides, two straight sides, which are the radii, and one arc. A segment only has two sides, one chord and one arc. Okay, segment only has two sides. A sector has three sides, including two radius and one arc length like that. Okay, now that we understand that, there are some properties of circles, angle properties of circles that we need to know about. Let's talk about those properties one by one now. Number one. Now, for each of these properties, what I'm going to do is I'm going to write down the property and I'm going to write down how to spot that property. Okay, so that you can remember how to spot that. The first property. How do you know you have to use this? You would have a tangent to the circle. A tangent to the circle at a point, and a radius drawn from the center to the same point. This is the condition for this first property. What happens in this case when you have these two things true? Let me draw that here. You have a tangent at a point, so it might look like this. This is the tangent. And at the same point, if you have a radius coming from the center of the circle, the angle between the radius and the tangent, that is always 90 degrees. This angle is 90. So this property is known as, in short form, we write it like this. We say radius is perpendicular to tangent. Or let me actually just write it fully in case this is confusing. Radius is perpendicular to tangent. But it has to be at the same point. So if this point is, let's say, x, the radius and the tangent, they should be drawn from the same point, right? So we have a tangent at a particular point and the radius at that same point coming from the center of the circle, they are going to be perpendicular to each other. This angle is always going to be 90 degrees. Okay, that's the simplest of all of these properties. Radius and tangent, they make a 90 degrees with each other. All right, that's the first one. This is the property. Radius is perpendicular to tangent. What I'll do is I'll do it the other way around. So I have this written here and the property written on top. Okay, so radius is perpendicular to tangent. How do you know that you have to use this? You have a tangent at a particular point and a radius at that same point. Okay, so that's the first property. Next, let's say you have a chord in a circle that looks like this. If there's a line coming from the center of the circle to this chord, such that it cuts the chord at the midpoint. Let's call this chord AB. And let's say this point is M. Okay, the point is M and the chord is AB. If this chord cuts this at the midpoint, the angle here is going to be 90 degrees. Okay, the angle here is going to be 90 degrees. Now, let's write that down. What's the property? If a chord is cut into half, by a line coming from the center, the angle made at that point is 90 degrees. This is always perpendicular like this, coming from the center. And it also works the other way around. What does that mean? If you know that the angle is 90, for this line coming from the center of the circle, then you would know that that chord is divided into half. Let me write that down here as well. If a line coming from the center makes a 90 degrees with a chord, the chord will be cut into half at that point. I can say that point would be the midpoint of the chord. That point will be the midpoint of that chord. Now let me explain it using this diagram. If you know that the angle that this line is making with the chord is 90 degrees, then you know for sure that these two sides are equal to each other. And the other way around is, if you know that these sides are equal to each other, then the angle made is 90, right? So if you know one thing, it implies the other. Okay, if you know one of those things, it implies the other. The other also has to be true. Now, how do you spot this? Basically, you either have a 90 degrees and then you say these sides have to be equal, or you have these sides equal and you say that the angle is 90, right? So that's basically included in how the property is described, that either you spot for the 90 degrees angle, or you spot that the chord is divided into equal halves, equal parts, like this. That's the second property. Now, the numbering is not important. You can do it in any order, it doesn't really matter. But now, the next one, the third property. Number 3 is, now this property is known as angles in the same segment, they're equal. Now, I'll explain what that means. Angles in the same segment, they're equal. Now, what does that mean? If we have a chord that looks like this, so any chord in a circle, and this chord now divides the circle into two parts, right? There's one segment on this side, that's the major segment, and this is the minor segment. If you have angles made by this chord in the same segment, so that means either in the major segment or in the minor segment, they will be equal to each other. Now, which angles are we talking about? Angle made on the circumference by a chord. For example, this is the chord. Let's label this something. Let's say this is A, this is B. This chord AB is making this angle at the circumference. And let's say the same chord is also making this angle at the circumference on that same side. And this chord is also making this angle at the circumference. All of these angles, if one is x, this is also x, this is also x. If you have a chord like this that makes angle at the circumference, these angles are all going to be equal to each other. Okay. Now, how do you spot this? So this property is known as angles in the same segment are equal. How do you spot this? You have angles or lines coming angles made at the circumference by the endpoints of a chord. So you have a chord like this. In this case, I drew this chord in green, let's say. And this is the chord that we're talking about. This chord, the endpoints of this chord, they are making some angles at the circumference. There's this angle here, there's this angle here, there's this angle here. These angles are all going to be equal. Okay? So whenever you have angles made at the circumference by the endpoints of a chord, they are all going to be equal to each other. Make sense? Let's take another example of this. This is one way to look at it. Sometimes you could have it in the smaller segment as well. If this is the circle, in this circle, let's say we have a chord that looks like this. Again, the angles could also be in the smaller segment. So this chord's endpoints are making an angle here. This chord's endpoints are also making an angle here, let's say. These angles are also going to be equal to each other. So this small angle here and this angle here, these are equal to each other. But they're not going to be equal to the angle on the other side. If there was an angle here on the other side. That would not be the same as that. These would be same with each other. They would be equal to each other, but not equal to the one on the other side. Let's actually call them something else. Let's call them y. These two are equal to each other, and these two are equal to each other. Okay? Because the angles y are in the same segment according to that green line, and the angles x here are in the same segment with each other. That's a different one. Okay? Now, in this case, you might have one angle given, for instance. They might tell you that this angle is, for instance, 40 degrees. Then what about this other angle? That should also be 40 degrees. Right? That's how this property will be used. Okay, let's move on. So that's the second one. Angles in, the third one, angles in the same segment are equal. Let's move on. Next one. Next is number 4. Angle at center is twice the angle at circumference. Angle at center is twice the angle at circumference. Now, what does that mean? Let's say you have a chord that looks like this. And the end points of the chord, they are making an angle at the center. Let's say that's happening like this. And those same points are making an angle at the circumference. Let's say like this. Now, if this angle is x, the angle at the center is going to be 2 times x. So the angle at the center is twice the angle at the circumference. Now, again, how do you spot? You would have angle made or angles made by the endpoints of a chord to the center and to the circumference. So you have endpoints of the chord. Let's call this chord AB. So you have angles coming from A and B. One is at the center, another is at the circumference. The one at the center is going to be 2 times the one at the circumference. Okay. Now, if there was another one at the circumference, it might be like this. This is also going to be X. If the one at top was X, this is also X using the earlier property. Angles in the same segment made by the same chord, they're equal. So these are equal to each other. And according to this property as well, if the angle at center is 2 times X, this angle is supposed to be X. Okay? Angle at center is twice the angle at the circumference. Now, sometimes you will see a relatively harder one in this, in which they will tell you something like this, that let's say you have a chord like this, and you know that this angle here is, let's say, 260 degrees. And they ask you to find this particular angle. Now, how can you do that? You look at this chord AB. This chord is making one angle at the center. That's this angle. How do you find this angle? Angle in a full circle is 360. 360 minus this 260. That leaves you with 100 here. If this is 100, this angle here is going to be half of 100. That means 100 over 2, and that gives you 50 degrees. So this angle here should be 50 degrees for that reason. Okay. So angle at center is twice the angle at the circumference. Okay, let's move on. That was the fourth one. Next. Angle made by diameter on the circumference is 90. Now, what do you mean by diameter? It means angle made by the end points of the diameter. On the circumference, that is equal to 90. So if you have a diameter, what's a diameter? It's a chord that passes through the center of the circle. So this line, for instance, you can say that's the diameter. The endpoints of this diameter, if they make any angle at the circumference, any angle of the circumference, let's say this is A, this is B. Let's say you have one angle at the circumference that looks like this. This angle is going to be 90. Now this chord might be making another angle on the circumference. Let's say that's here. This is also 90. You can make another angle. Let's say that's here. At the circumference coming from the ends of the chord, this is also 90. So angle made by a diameter on the circumference of a circle, this is always equal to 90 degrees. All right. That's another one that you need to remember. Angle made by the endpoints of a diameter on the circumference, that is equal to 90 degrees. Okay. The next one. Number 6. In a cyclic quadrilateral, opposite angles add up to 180. We call these supplementary angles. Angles that add up to 180, there's a name that we have for them. They're supplementary angles. Now, what's a cyclic quadrilateral? A cyclic quadrilateral is one that has all its vertices on the circumference. A quadrilateral having all its vertices at the circumference. Now, what does that mean? Let's take an example of this. Let's say we have the circle, and on the circle, we have a quadrilateral that looks like this: 1, 2, 3, 4. We have 4 sides. It's a cyclic quadrilateral. All of these vertices are on the circumference. Let's say this is point A, this is point B, this is C, this is D. Now, if this angle is X, or let's call this W, let's say this is X, this is Y, and this is Z. The opposite angles, their sum is going to be 180. So W plus Y, that is going to be 180. And X plus Z, that is also going to be 180. So if you have any quadrilateral in a circle, any cyclic quadrilateral, the opposite angles, they will always add up to 180 degrees. Okay, the opposite angles, they always add up to 180 degrees. Okay, that was the sixth one. Let's move on. Now, this is a very important one, used quite a lot. Tangents coming from outside a circle. Tangents coming from a point outside a circle. Now, what happens in this case? Let's say we have a circle like this, and there's a point outside the circle. Maybe that's here. And there are 2 tangents coming from that point. There's one tangent that goes like this, and there's another tangent that goes like this. Now, these 2 tangents are going to be equal to each other. These 2 tangents, they are equal to each other. Let's call this point something. Let's say that the point outside the circle, this is point A, and it's touching the circle, or let's call this point X. It's touching the circle at point Y, and it's touching the circle at the point Z. And the center of the circle is C. Now, whenever you have a shape like this, you need to remember, number one, so there are a lot of things that are true in this. Number one, X, Y, this tangent, and the other tangent XZ, they are equal to each other. Okay? That's the main property. X, Y, and XZ, they are equal to each other. But they also follow a number of other things from this. And what are those other things? Whenever you have a figure, whenever you have 2 tangents like this, what you would always do would be, you would join these points with the center of the circle as well. So you'll join those points like this with the center on this side, and similarly here on this side. You will join Y and Z with the center of the circle. Now, when you do that, what are these 2 sides? These are radius. These are both radii. This is R, this is R. These 2 sides are equal to each other. And we know that this angle and this angle, they're 90 degrees. Why? Because now we have a radius here and a tangent here. We did this property above. At a point, if we have a radius and a tangent, they are perpendicular to each other. So we have a kite like this, and it's a kite such that if I were to divide this kite into two parts like this, I get two congruent triangles. These two triangles are going to be congruent. Let me write that down here. X, Y, C, Z, this is always going to be a kite. Now, if you have a kite like this, and you divide a kite in the middle like this, you always get two equal triangles, two congruent triangles. The triangles XYZ and the triangle XZC, they are going to be congruent triangles. What does that mean? Since we know that this side is equal to this side is equal to this side, two sides are equal, the third side is common. So these are congruent triangles. Now, this angle, that means if we call this X, is equal to this angle. This angle here, let's call this Y, this is also equal to this angle. These two angles are going to be equal to each other as well. So all the angles are going to be equal like this. If this is X, this is also X. And if this is Y, this is also Y. And the sides are also going to be equal. Okay. So this is a property when you have tangents coming from a point outside a circle, these two tangents are equal. That's the main property. But then all of this follows from this, that you get a kite-like figure here. And if you were to divide that kite into two parts like this, the two angles here, they're equal, and the two angles here, they're also equal. And also, if you were to add up this whole angle and this whole angle, they also add up to 180. So you can say 2x, this angle, plus 2y, this whole angle. Both of them add up to 180y because these are 90. The sum of all angles has to be 360 here. It's a quadrilateral. Kite is a quadrilateral that has 360 degrees total angle. If these two are 90, that means their sum is 180. The sum of the other two angles, that's also going to be 180. So if we add up those angles, the result turns out to be 180. That's this property of kite. Tangents coming from outside a circle, from a point outside a circle. All right. Okay. Next. This property is known as the alternate segment theorem. Now, this did not used to be part of the syllabus before, but now it is part of the syllabus. It's called the alternate segment theorem. Now, when you have this alternate segment, how do you spot this? In this case, you would have a tangent at any point. Let's say that looks like this. So you'd have a tangent. And from this point, you would have a triangle in the circle anywhere that includes this point as one of the vertices. So let's say you have a triangle like this. This is a cyclic triangle because all the three sides of this triangle, they are on the circumference. Just like we had a cyclic quadrilateral, we can say this is a cyclic triangle. So how do you spot this? You would have a cyclic triangle and you would have a tangent. You would have a tangent at one of the vertices of the triangle. Okay, so we have a cyclic triangle, and you have a tangent at one of that's touching one of the vertices of the triangle. Now, what happens in a case in something when you have something like this? Let's call this point A, let's call this point B, and let's call this point C. In a situation like this, the angle that this chord makes with the tangent, if this is x, the opposite interior angle of that triangle, that is also going to be x. What happens in this case? The angle between one of the sides of the triangle and tangent is equal to the interior angle opposite to that side. Now, let me explain that using this triangle. We have this angle x here. So we have this tangent going outside, and we have a triangle inside like this. If this angle here is x, this is the angle made by this side with the tangent outside. If this angle is x, the angle that is opposite to this side, opposite to the screen side, inside the triangle, that is also going to be x. And if we talk about the other angle, this angle here, let's call this y. This is the angle between this orange side of the triangle and the tangent. It's the angle between the orange side of the triangle and the tangent. This angle y, this is going to be equal to the opposite interior angle of the triangle, and that's this angle here. This is also going to be y. Okay? These angles are going to be equal to each other. This is called alternate segment theorem. This is how you spot this. You would have a cyclic triangle, and you would have a tangent at one of the vertices of the triangles. This is a tangent. The angle that a side makes with the tangent is this going to be the same as the angle on the opposite side of the triangle, the opposite interior angle. These two angles are going to be equal. This is called alternate segment theorem. These are all the circle properties that you need to be aware of. And now when you look at questions, there will be one more thing that you will notice that you'll be using a lot that you should also know. It's not a circle property as such, but it's just something that you also need to remember. And that is, when you have a circle like this, and you have a triangle that has two sides that are the radius of the circle, and the third side is some chord. This is going to be an isosceles triangle. Why? Because if two sides are radius, then whatever the other side is, we have two sides equal. This is going to be an isosceles triangle. Okay? When you have an isosceles triangle, what that means is the opposite angles here, they're going to be equal. If this angle is something, the opposite angle here is also going to be the same thing. So if one of these is x, the other is also going to be x. These are going to be equal to each other. Sometimes you have to use this as well. When you have a triangle like this, it's an isosceles triangle. do keep this in mind when you're working with circle problems. Okay. Now, in the next class, we will look at some examples on this and also look at the next next small topic. We'll try to cover that in the next class as well. But this topic does require a lot of practice. I'll be uploading a worksheet by tonight, inshallah, a couple of worksheets that you can start working on. We will be doing questions from that worksheet in the next class. You can also let me know any problems that you have from the worksheet. You can ask about them in the next class. But before that, you need to have attempted many of them so that you know where you're having problems, and we will discuss some of them in the next class then. Okay. Now, the next few topics, apart from a couple of small topics that we might add in the middle, they're going to be major topics like vectors, transformations, mensuration. These are some of the next few topics that we'll be doing. We'll do daily math topics in the middle, depending on how much time we have in a particular class. If we finish the topic early someday, we might do a small topic alongside in that particular class. But we first want to do the major topics now. We'll try to get done with them by the second week of March, inshallah, so that the smaller topics that we're left with then, we can then after that cover them gradually as well. Okay, that's it for today. I'll see you again in the next class. Please make sure to attend questions from the worksheet. We will be doing more practice from this in the next class then. Okay, all right. Allah Hafiz.